So till now, we saw swapping, but let us try to see exactly the concept that we understood was theoretical. Now, can we see that not as a concept, but let us see like how exactly that swapping can be visualized or seen rather live on Linux operating system. So for that purpose, I would be writing a program, okay, using C, and then we'll try to understand what exactly that. So let us make OS to do it in front of us. So we cannot directly tell Linux swap the process, but we can do something smarter. By creating the memory pressure, we'll force the operating system to move processes in and out of RAM. Okay, so we have to write first a trigger program which will force the swapping. Okay, so let me write Emacs swapping.c ampersand. So I'll be using including files here as input stdio.h as stdio.h as input stdio. If required, we'll add few more ones. So let me define some memory like 100 MB space, like using as define. Sorry, as define. Let me declare size by writing this 1024 multiplied by 1024 multiplied by 100. So I'm reserving 100 MB space. Fine. Now I would be using some standard system calls. Okay, and kind of functions too. So the main. So first of all, I will be printing printf process PID or process ID, you can say, is %d slash n double quotes get PID. Correct. Now, what we'll do is we'll keep doing the things internally. So let me write the code, then I will explain side by side. Like once code is done. Okay, so while one void star pointer equal to alloc. Now I'm writing directly allocating that size for pointer total 100 MB space. So if pointer equal to null, then print printf failed. Fine. And then right here terminate the loop while. Fine. Fine. Otherwise, we'll touch memory to ensure allocation is real. Okay. So uh, let me write for I equal to I integer I equal to 0, I less than size I plus equal to, we'll add 4096 every time. Okay, so that we can ensure allocation is real. Okay. Let me type in this and then I will explain what exactly I'm doing. PTR I complete and then it will write printf did. So depending upon RAM that you have, that code can change. Okay. So currently, like my laptop has more RAM. So let us see like how exactly we can get this done. I can complete this for while and then return 0. Now this program is doing something very simple but powerful. So what I'm doing is here, it keeps allocating memory continuously. It touches memory to force real allocation and it never frees the memory. So memory usage keeps increasing because we wrote that code inside while one. Am I right? So memory usage keeps increasing, and at some point, what will happen? RAM becomes full. So OS has no choice now. It starts swapping process to the disk. Okay. So if you see, like if at all, let me execute this, and then we'll try to understand what exactly happened. Fine. So let me save this code. Let me write cc dash m32 swapping. Fine. So let me execute it. Correct the errors. So let me go back to the code and let me explain what exactly I did. So I initially added three header files. Okay, then I declared 100 MB so that each allocation would be of size 100 MB. So we are not allocating small memory. We are aggressively consuming memory. Okay, this is the thing. Then we are printing the PID. Okay, to print to get process ID. So we use this PID to track the process in like Linux tools like /proc or some other tools. Then we are executing an infinite loop. Okay, so that the program runs forever and keeps allocating memory continuously. So there is no stopping condition, memory usage will keep increasing. Then we are having a void pointer, malloc says 100 MB of memory each time once the code, once the loop gets executed. So Linux uses lazy allocation. So memory is not actually used until accessed. So we have to write allocation check. So for allocation check, we are checking pointer equal to null. If memory fails, program stops. So this happens when system cannot allocate memory. Get this one. Fine. Then we are forcing real memory usage, and this is very important. So what we did was we wrote a for loop, and then we are applying. This is most important part of our program. So OS allocates memory in pages, like usually 4 KB. That means 4096 bytes. So we touch 1 byte per page. So this forces actual physical memory allocation, and it's not just like virtual allocation. So without this loop, swapping may not happen, and that's why we have added this. So because memory is not actually used. Then we said like once that loop is done, it shows only the progress for to us, like allocated 100 MB. Each time it shows this allocated 100 MB, that means it is actually doing the work. And then we are waiting for 1 second. This slows down allocation so we can observe swapping live. And what would be happening here? Allocate 100 MB, force real memory usage, repeat forever, RAM fills up, and OS starts swapping. So this program does not implement swapping, but it forces the operating system to perform swapping. Fine. So as program runs, RAM fills up, swap starts increasing, okay, and system slows down. And this is exactly what we want to demonstrate. Fine. So what is the thing that is happening? Continuous allocation actually will force OS as a to react by saying memory pressure. Then touching memory, we are using real RAM usage. RAM full, swapping begins. Too much pressure, that means thrashing disk. So this program is not about code. It is about triggering a real operating system behavior. So let us try to execute this code, and then we will see exactly what is happening. Fine. So let us save. Okay, and then let us shift and then execute. Dot slash a.o. Let us see this. So it did this allocated MB, allocated MB. Now I will open another terminal and I will write htop command. Correct. Now look for swap usage increasing. Like okay, so we'll see that you can see the swap SWP. Correct. It is increasing. 124 MB, then 241 MB, then 340 MB. Right? So memory is becoming full. Swap usage is increasing. You can check this scrolling that is happening. Now the system is under pressure. Like it is showing us red in red. Like you can see different things. Correct? Like now, what we are saying, we are starting to move out the process out. Fine. Now let me go back and let me write b dash h. Now you can see memory allocation failed. That means somewhere it is not permitting us to create that part. So if I again execute, what we'll do is we'll use a counter there inside the code so that we can see how much things are done. Okay, now you can see my machine slowed down ultimately. I am pressing arrow keys. Teacher, yeah, we'll say how. Okay. Assign this as one. So as to see like what is happening. So how many allocations are done, right? So let us compile. You can see like my machine is under still some pressure, right? Let me execute this. Fine. And let me go back to the terminal. You can see the contiguous memory allocation. The memory allocation is continued. Now, if I go back to htop, check the things. Okay, so we'll stop this code. Then we'll see whether what is the output of htop. Okay, let it simply slow down. There is still memory available. Okay, swap space is taken. So it would be doing that tasks side by side. It will release it depending upon like if at all necessary. Right now it is under pressure. That's what you can see. This thing RAM is increasing. This is memory. RAM is increasing. Swap RAM is decreasing. Swap is increasing. That's how you would be seeing afterwards. Okay. So let me execute this code. Let us concentrate on this. You can see 2.80G, then 3.83, 3.17. Okay, still till that time this RAM, this memory remains same. Correct. Now 3.8. So when it reaches to that 4, okay, check this. Now once it reaches to that limit, RAM is RAM will start decreasing, and then this will start increasing. Okay, once it passes that limit of RAM, concentrate on these values: 5.3, 985, 5.6, 5.7. This is 985 still below 6.0. Now you can see, so it stopped there. Now you will realize RAM is getting decreased. Correct. So 2 point. Then already swapping started with 1.2, 1.21. Right. So RAM is considered here like 70, 35, 39, and so on. Now once it stopped, you can see when it stops, ultimately your code gets running. So that was the moment when the swapping began. Correct. So you can again check this with vmstat. So let me do it again. We can check this thing with vmstat. Okay, you can see like here you would be seeing SI, that is swap in and swap out. SO is swap out. Now, if there are these numbers increase, if you can see swap in and swap out. If these number exist increase, swapping is actively happening. You will at one point of time you would be seeing that. Correct. Swap in is happening. Swap in is happening. Correct. Swap already started. Correct. 102. Swap out hasn't happened. Correct. Yet. So this is just we're trying to visualize this. Like you can see swap out happened. So 9, that was the big number, then swap out happened. And at one point of time, the program stopped. Correct. So now you would be seeing that it would be slowing down. Now the command that we used here, like if I see, we used vmstat. So if I write vmstat, this is for virtual memory statistics, okay, which we used to really see what is how that's happening is. So similarly, one can do this with other commands too. So let me execute this. Okay, then we'll write here ps -ejh. You just get that a dot out. So process number is 10062. So if I write cat slash proc slash 10062 slash status. Fine. Now you will see there, like try to see VM swap. You can see VM swap, correct? Like it was 0. If I go back and check it again, VM swap, VM swap. So code must have stopped there, that side. Yeah. So that's why. See, so this you can try this by having executing this code, the command which I showed you. Look for stuff. So this shows how much of this process is swapped out, that particular count. Correct. So if you can minimize that 100 MB storage, okay, then you can again check it. Like for example, let me go back and let me try 10149. So VM swap, it is showing 0 KB still. This is the place we are concentrating on. If at all swapping happens there, then it shows us. Okay. Actually, how many times this process was swapped out. So right now, nothing has been swapped out. Reaching to some level. Yeah. So the program is getting terminated. So what we did was we used htop. Okay, we showed swap increasing. Okay, and we saw vmstat also there. So now you are imagining swapping. You are actually watching it happening live. Swapping is not free. As swap increases, system slows down. Disk activity increases and CPU may wait. So it is, if pushed further, this can lead to thrashing. So what just happened was RAM got full, OS moved out process to disk and new allocation continued. This is swapping in action. So we don't ask the OS to swap. OS created pressure and the OS responded. Don't like I suggest you this thing, like don't run on low RAM systems without caution. Correct. So stop program with kill using -9. So if I check, my program must have got terminated. Right. So otherwise use kill -9 to terminate that process. Like if you have small RAM, because otherwise it will crash or it will collapse your operating system. Fine. Thank you very much.